we're going to talk about logarithms today. I've given you the definition. If we let b and y be positive numbers where b is not equal to 1, the logarithm of y with base b is denoted as, and we read that, log base b of y. And it's defined as follows. Log base b of y is equal to x if and only if b to the x equals y. So what that is saying is, if I give you a sentence in logarithmic form, which is, let's take a sentence, log base 2 of 32 is equal to 5. This sentence, as an exponential sentence or an exponential form, means 2 raised to the 5th power is equal to 32. So the little 2 here is called the base, and this 32, which is the same size as the log, is called the argument of the logarithm. And the base and the argument always must be positive. Base and the argument always must be a positive number other than 1. Okay. Okay, let's take another sentence. This sentence is a sentence that is an logarithmic form. And if we rewrite it in, if we rewrite it as an exponential sentence, it means 10 to the 1st power is equal to 10. So what we do, if we start with the little base and we go around in a circle, 10 to the 1st power is equal to 10. So a logarithm, notice the logarithm is equal to the exponent. So what is a logarithm? A logarithm is an exponent. It's a way to express an exponent. 10 to the 1st power equals 10. Notice the logarithm, log base 10 of 10, is equal to 1. Okay. Alright, so we can evaluate some logarithms knowing that. Evaluate means to find the value of. We can evaluate log base 3 of 9. Log base 3 of 9 is an expression for a logarithm, which is an exponent. Remember, a logarithm is an exponent. So when I evaluate a logarithm, I'm finding an exponent. This logarithm means, remember, the little 3 is called the base. The 9 is called the argument. And that's what the power is equal to when I raise 3 to an exponent. This is saying 3 raised to the what power equals 9. And the answer is 2. So the value of this logarithm is 2. One more. Log base 5 of 1 over 25. This logarithm says log base 5 of 1 over 25. And what it means is, remember, a logarithm is an exponent. So we're looking for an exponent. It means 5 to the what power equals 1 over 25. And the answer to that would be negative 2. How did I know the exponent was negative? Because of the 1 over. Remember, if we flip the fraction, it means our exponent's negative. Okay? Another thing we can do is we can find the inverse of a logarithmic function. Notice it's a function because it's got 2 variables where y depends on x. Also, it's got a logarithm in it, so it's a logarithmic function. So how do we find the inverse of any function? We switch the x and the y, and we solve for y. And notice I have over to the right, in order to solve for y, we're going to need to rewrite it in exponential form, just like we just did. So the first thing we're going to do is we're going to switch the x and the y, because that is the definition of inverse function. And then lastly, we're going to solve for y by rewriting the function in exponential form. So we're going to start with our base is 5, and we're going to raise it to the x power, and that's equal to y. So there, we did it. We solved for y. Y equals 5 to the x. Okay, let's do another one. Y equals the ln of x minus 10. Okay, the first thing we're going to do is we're going to switch our x and our y. And now we're going to solve for y. So we're going to rewrite it as an exponential sentence. Remember, ln stands for log base e. So this sentence is saying e to the x power equals y minus 10. And we're almost finished solving for y. All we have left to do is add 10. So the inverse of this log function is y equals e to the x plus 10, which notice is an exponential function. Every time we find the inverse of a log function, we're going to get an exponential function. Okay, let's do one more. X equals log base 3 of y plus 2. So we're going to we switched the x and the y, now we're going to solve for y, so we're going to say 3 raised to the x power equals y plus 2. So we're going to subtract 2 and get 3 to the x minus 2. Okay, so the last thing we're going to do is we're going to look at this log function, this last one, number 3, and we're going to talk about the graph. Remember, log functions are the inverse of exponential functions. So if we know something about an exponential function, then we also know something about a log function. Okay, so we know that a log function has, instead of a horizontal asymptote, it has a vertical asymptote. It has a domain. All functions have a domain and a range. And instead of finding a y-intercept, we're going to find an x-intercept here. Okay? And then we're going to draw a sketch. Okay, so if I look at the function y equals log base 3 of x plus 2, I notice that we have a horizontal shift to the left too. So instead of there being a vertical asymptote at x equals 0, there's going to be a vertical asymptote at x equals negative 2. So I'm going to draw it. So we have an asymptote at x equals negative 2. And the graph will always stay to the right of this asymptote. And so the domain will be greater than negative 2 here. And the range of all log functions, and this is just something you can go ahead and memorize, the range of all log functions would be any real number. We'll always go forever up, forever down. And then lastly, we're going to find the x-intercept. The x-intercept is what we get when we make the y 0 and solve for x. So let's do that. Okay, I'm going to make the y 0, solve for x. I'm going to say 3 to the 0 power equals x plus 2. 3 to the 0 power is 1. And when I subtract 2 from both sides, I get negative 1. So we've got an x-intercept at negative 1. We've got a graph that approaches the asymptote and curves this way. So if you notice, it looks just like the exponential function, 3 to the x minus 2. Since it is its inverse, it is just like it, except it's kind of flipped over on its side, if you notice that. Okay,